Working. We're pleased to welcome Ryan Anderson, giving us a talk today on spectroscopy for all, SuperCam chemistry, open source software, and accessible education. We can see your slides just fine. I think we can hear you okay, Ryan. So why don't you take it away? Thanks for being here.
Okay, yeah, thanks for having me. I'm excited to share this with all of you. When I was thinking of what to talk about for this talk, it sort of occurred to me that the three sort of major areas of my work overlap in that I'm trying to make spectroscopy available for people in one way or another. And so I thought I'd start on this slide. This is a graphic that I made for the SuperCam team for our press release. This is our first spectrum from Mars from a few years ago. And it's full of technical information, but also tried to make it friendly enough and appealing enough that people would actually want to look at it. So I'll get started. So the three sort of categories that I'm going to talk about. First is my work on SuperCam and ChemCam, especially working on the quantification, going from spectrum to chemistry. That kind of naturally leads into my work on this software tool, PyHAT. It's an open source tool to do spectroscopy analysis. And then I'll finish up with the Planets project, which is an education project that we've been working on for quite some time. And that project also involves spectra and, how do you teach kids about spectra, and then how do you take that a step further and teach kids with different abilities, such as blind kids, about something that's so visual as spectra. So that's sort of the layout of the talk. So I'll just jump right into the SuperCam and ChemCam stuff. So this is a major part of my work. I spend a lot of my time on this work. And the idea is we want to use these laser-induced breakdown spectroscopy instruments to analyze rocks on the surface, and they return an atomic emission spectrum like the one I showed on the first slide and the one shown here. And we want to take that spectrum and determine what the chemical composition of the target is. What are the major oxides in that rock? And you might think it's simple enough. You just measure how tall the sodium peak is and you know how much sodium there is, but it's a little more subtle than that. So we do a lot of work on this, and those results are one of the key products from the instruments. Those go on the PDS and are used by people doing geochemistry on the rover targets. So we really want to get this right to the best of our ability, and it's a challenging task. So I think most people are familiar with LIBS at this point, but in case you're not, or in case you want a refresher, LIBS is laser-induced breakdown spectroscopy. So we target at a distance, we fire a very intense laser pulse and ablate it. And on the right here, you can see some actual photographs of LIBS plasmas in the lab. And you collect the light from the plasma, and you can see even in the photograph, the colors are different. And as we all know, emission spectra tell you what atoms are in the thing that is emitting. So we would love it if we could just do a simple first principles physics calculation and get the quantity of the elements that are emitting. The problem is the integration of the instrument. We collect data over the whole lifetime of the spark. And so it's not in equilibrium. We have a rapidly changing plasma temperature, density, opacity, and also inside that little ball of plasma, all the atoms are interacting with each other. So you get really complicated effects that are hard/impossible to understand, where the concentration of one element will influence the emission strength of a different element. And so basically we're left having to resort to an empirical calibration where we take a ton of spectra in the lab, feed those into a statistical model, and use that to predict the composition of spectra of unknown targets. So essentially, it's a regression problem. You have a bunch of X variables, that's your spectrum, and you're trying to predict a Y variable, that's your composition. And so we do this, like I said, based on samples with known compositions where we have the spectrum and the elemental composition in the lab. And we use root mean squared error to evaluate it. For those who remember their intro statistics, this is almost the exact same formula as standard deviation. It's just the deviation from the correct answer rather than the deviation from the mean. And so this is the standard way of measuring accuracy on a problem like this. It has some nice properties that help us use it to assess the models. And then we talk about different flavors of RMSE. RMSE-C, the RMSE of the calibration set, is what you use when you're talking about you've trained a model on a certain data set and then you predict that exact data. And RMSE-C is kind of cheating. Like you're always going to get a good answer because you trained on that data. RMSE-CV is when you predict held out data during cross-validation. That's when you're tuning the model. And then RMSE-P is what we really use to assess the accuracy of the model. And I sort of belabor this because people get mixed up and talk about one when they mean the other. And it can trip you up and you can end up talking about an accuracy that doesn't actually tell you what you think it's telling you. So these models that we make are multivariate regression models. That means we're using information from the whole spectrum or many parts of the spectrum, not just a single emission line from a single element to predict its composition. And doing this is beneficial because it corrects for what we call matrix effects. That's all the sort of unknowns about how the atoms interact with each other, the conditions of the observation, things like that. There are lots of different approaches for this, many different algorithms. They all solve the basic same problem using different approaches. And I wish I could tell you there's one that's just always the best, and it is never that simple, right? There's many different algorithms, and one might be great for silicon, but totally fail for sodium. And so we try a bunch of them and then compare the RMS-EPs to narrow down to our favorite models. So this is sort of an alphabet soup of the different types of models. I won't read this all off, but suffice it to say there are many, and we try as many as we can. This list is a little longer than what we currently use. We've found that some of these just consistently are not as good, so we have pared this down a little bit, but there's a lot to choose from. In our efforts for SuperCam, we've also we have a current calibration that's okay, but it's not perfect. We know there are some issues with it, and so we're working on a new SuperCam calibration that uses an expanded database. When in doubt on this sort of problem, the more data you have, the better to feed into these models. And so this new database includes data shot at different distances and different focuses, so you can get some of those varying effects folded into the model. And it also greatly just increases the number of samples we have. So you can see on these log plots, the new are in blue, wherever there's blue sticking out above the red bar, that means we have more samples at that composition. So you can see we've really fleshed out our composition ranges. Titanium, for example, we had basically nothing except one very high point. We've filled in that gap so we can actually predict high titanium now. Our previous model was restricted to the low end, things like that. So we have a ton of new data, and we're feeding it through all these regressors to figure out how we can get the best compositions. So given the database, we split it up into what are called folds. These are subsets of the data set with a similar distribution. And we get that similar distribution by a very simple method. We just sort on the element that we're trying to predict. So if you're predicting silicon, you sort on silicon, you assign the lowest to fold 1, the next lowest to fold 2, and so on, and you iterate around. So each fold has about the same distribution. There's some spikes in here because we have many duplicates of certain calibration target samples that get folded in there, but overall you get a similar distribution. We then set aside one fold as a test set. That is completely, the models are completely blind to that set. The rest of the folds are used for cross-validation, and that's where we're tuning the parameters of the models to get the best possible prediction. We then bring back the test set and use the tuned models to predict it, and that's how we get that final accuracy estimate. So cross-validation, you may or may not know what it means, but it's basically the machine learning version of what happens when you overfit a polynomial. So the top is a linear trend in data with noise. And you can see if you use a really complicated model, a high order polynomial, you can get a perfect fit. But then you get a new data point and it gives you a crazy answer. That's not what we don't want that to happen. We want to find the simplest model that gives a pretty good answer. And so that would be in the top, that would be a linear fit, not a multi-order polynomial. Same idea with all of these machine learning models, one way or another. The bottom example is partially squares. This is a fairly simple machine learning model, but one that is pretty good. And you can see the RMSEC, that's the result where you predict the data you've been training on. That just gets better and better and better as you get a more complex model. But at a certain point, your RMSECV, that's where you're predicting those held out folds, that kind of flattens out. It stops improving with model complexity. And that's where you want to pick. So for different models, we try to optimize the parameters so that we're not overfitting, and we get good predictions on unknown data, not just on the training set. And a new innovation that we're working on for the SuperCam calibration is we are using cross-validation now to tune not just the parameters of the regressor, but also all of the pre-processing steps that go into the spectrum. Do we normalize it this way or that way? Do we do feature selection? How many features do we select? All of those things. We found a way to kind of fold that all into one sort of pipeline, and we can optimize that with cross-validation. It takes the guesswork out, because before we would sort of manually change those pre-processing steps and then run cross-validation on each one of them. Now it's all folded into one big optimization problem. The problem with that is that it gives you a huge search space. This table, we don't have to read the whole thing, but there's a bunch of different ways you can normalize the spectra, a bunch of different ways you can mask it, different ways to do feature selection. You can bin the peaks to reduce the number of spectral channels, all these sorts of things, not to mention all of the different parameters for each regressor. Multiply all this together, you get millions of potential combinations. You have to find an efficient way to search that space. You can't just kind of blindly try every possible permutation. So we are using a new way of doing this. We're not just doing what's called a grid search, which is sort of the old way where you just try every possible permutation. That in the literature has been proven to not only be slower, it's also not as good. You can see in this figure in the top that kind of illustrates it. If you have two parameters that control the results of your model, and these sort of colored squiggles are how good your model is, if you have a grid layout, you are missing a lot of settings of each parameter. You're just getting a few in each direction. If you switch to a random selection of settings, you kind of think random would be worse, but it's not. It's better, because you get these intermediate values that then give you results closer to the best solution. And it turns out if you do a Bayesian search where you're not just randomly picking permutations, but you're actually taking the results of your first iteration and intelligently choosing how to vary your parameters for the next step of the iteration, you get very good results faster. So the bottom right is sort of a proof of concept that I did, where I did a grid search, and then I did a Bayesian search on one of our models. And you can see they give very similar answers, but the Bayesian search spends much less time. It doesn't have to check all of these dots. It just bounces around and realizes, hey, look, the L1 parameter should be 1, and then we can just fine tune this other one and find the very best solution. So that's what we're using now, the Bayes search. It allows us to search this large parameter space efficiently and come up with pretty good models. We also have some tricks up our sleeve for making the models able to handle a whole lot of different target compositions. In the lab, if you read the literature, and there's papers about estimating the nickel content in steel, and that's a much simpler problem than estimating the composition of an unknown geologic target, because steel has a very constrained range of compositions. So your matrix effects really well. You can train it on a bunch of very specific targets, and you get really, really specific answers. We need to be prepared for anything. We don't know what Mars is going to throw at us. We might get a calcium sulfate vein one day and a pure manganese oxide the next day and a regular old basalt the next day. And so we need to be able to handle all of those. So one strategy that I came up with for ChemCam is this submodel blending approach, where it's hard to train a single model that can handle the entire compositional range of an element. But what we can do is we can train several models that specialize in certain ranges. So on the left here, you can see we have a low model, a mid model, and a high model. And they're terrible outside their training range. The high model, and anything below 60, it's just garbage, but it's very good at the high end. And if you take those models and you blend those together, you can actually end up with results as shown on the right, the red dots that are better than a single model, which are the black dots. So that's what we do for SuperCam, and we're using that sorry, that's what we do for ChemCam, and we're using that as one of our options for SuperCam. But another innovation that we're working on is this approach called stacked regression or superlearner. And so this is an alternative to submodel blending. Um, so what it does essentially is it takes the predictions from a bunch of other models and it feeds those into a sort of final model. So you may have 10 different models, some of them trained on 0 to 100%, some of them trained on just 0 to 5%. All those submodel ranges, you can have multiple models in each range, and you can kind of just dump all the results into a final regressor, and then that gets trained and optimized and allows you to combine those results in a more complex way than just sort of blending and doing a weighted mean to put the results together. So it has the advantage that you can use multiple favorite models per range, not just one. And you don't have to do any fiddling with the range over which they're blended or anything. You just tell it to optimize and it takes those inputs and gives you an output. And on the right is an example from a poster I presented last year of our initial new titanium model, where the top is the blended, the bottom is superlearner. They're not wildly different, but the superlearner is a bit better. And we're seeing that pretty consistently, that it tends to have a bit of an edge over the blended submodels. So it looks really promising. We're just in the process of choosing our favorite models for the rest of the major elements right now using these approaches. And this is what it looks like when we produce a model candidate. This is one of our titanium candidates from a while ago. It's not a finalist anymore, but this was a pretty good proof of concept that things were working. And so we use these different plots to assess how a model candidate is doing. So test set performance, test set if you shift the wavelength a little bit, because we know our wavelength shifts a little on Mars due to temperature. How do we do on the cal targets? How do we do at different distances? And then in our previous models, we've seen some strange behavior with shot-to-shot measurements where a model will jump from one prediction to another sort of instantaneously over repeated shots of the same location. And that's not normal. You want a sort of a smooth trend. So we have this plot that allows you to look at that. And finally, a plot that looks at how we do in terms of accuracy as a function of our focus. As we go out of focus, are we still getting acceptable results? So we put all of that together, and that sort of is our first way of assessing the models. And then we take them and do some sanity checks. Are we still predicting olivine as olivine? Does it fall within the accepted ranges for the certain minerals that we've detected with Raman or that we suspect are there from other lines of evidence? So that's the SuperCam and ChemCam work. And sort of out of that, a few years back, I started working on this tool called the PyHAT, the Python Hperspectral Analysis Tool. It's basically the tool I wish I had like 15 years ago when we started doing the ChemCam calibration. And I just decided I'm going to make this tool for myself and for anyone else who wants it, just to make it possible to do some of these things without having to spend years and years writing your own code and looking up how to implement certain multivariate regressors. So the idea is it provides a lot of these tools that we use to do the calibration, and it makes them available for people who are not programmers. So it can be, if you are a programmer, it can be imported as a library and incorporated into your own scripts. If you're not a programmer, it has a graphical interface. So you can just click buttons and choose from drop-down lists and do a lot. It's not quite up to date with our latest from SuperCam, but a lot of the pre-processing and regression and all of that stuff, PyHAT can do it. and you don't have to, invest a ton of your time and money on developing your own code. So it's been supported by a few PDARTs, a couple that I led, and then one that was led by Lisa Gaddis to add some band parameters and other things for hyperspectral imagers. We've also gotten a little bit of internal USGS funding and support from the SuperCam and ChemCam instruments. Currently, we have a bit of that USGS funding to do some data ingestion so that terrestrial remote sensing people who work with certain satellites or aerial platforms can easily read their data in. I'll show you on the next slide. The data format is quite simple, but if you're not a programmer, translating your satellite's particular data format into the PyHAT data format can still be a pain. So we're trying to simplify that for people. We also have a user guide. It's in the final stages of a very long and painful USGS publishing process, but that'll be coming out hopefully this year, and is sort of the one-stop shop. It has a lot of, it's not just like how you run the code. It's like, why would you want to run this regressor over this one, and what do they do? How do they work? That sort of stuff. So hopefully it's a good reference. I've been sending the draft version to people when they ask about PyHAT. So hopefully that'll come out soon and that can support the code. The PyHAT data format itself, as I said, is very simple. It just uses a CSV format. The key to the format is it has a 2-level column name. So this is like a really simple example of a set of spectra, and your wavelength data, your spectral data, it has a top level label that's all the same, and then the second level label is the individual band wavelength. So that allows you to do something like data set wavelength, and you get all the spectra, or you can say data set wavelength and then the specific number and get just that column. It's a nice, flexible, and simple format that lets us do a lot of useful things, and has the benefit of just being a human readable CSV file. And for data cubes, like hyperspectral images, it's a little bit clunky, but you can transform a data cube into this format. You just store your X and Y position in the cube as metadata, and then you can do work in PyHAT and then transform it back. That's a fairly new capability, but we're going to work on that and hopefully find a way to make it more efficient and faster. But it does work for CRISM and MQs and some other data sets. This is what the graphical interface looks like. The idea behind this was to try to make something that's nice and flexible. So the interface has a bunch of categories at the top, and then you choose what we call modules from those categories, and they appear in this central pane that is your workflow. And you can put them in any order. User beware, if you try to normalize, but you haven't loaded a spectrum yet, it's going to break. But within reason, you can do things in whatever order you want, and then you can save it out, which is a key aspect of this. You can save out the workflow as a JSON file, and then it can be restored next time. So you can work on it and then save it out and walk away and come back next time, or you can share it with someone, or you can just have the JSON file so that 2 years from now, when you don't remember what you did, you can go, even if you don't have PyHAT anymore, you can open up the JSON, it's human readable, and you can say, oh yeah, I normalized it this way, and then I did this. So the saving capability allows us to do all of this work and make it reproducible and transferable to other scientists. So this is basically what it looks like. This screenshot is a little bit out of date. Our load data has a few more options now, but this gives you the idea. Some of the things that PyHAT can do, we have a bunch of different data transformation methods. You can interpolate, you can shift the spectra, you can apply masks, normalize, standardize the spectrum, take the derivative, multiply by a vector, like if you're applying an instrument response. You can do peak binning, which is what's shown over here. This is a little trick that the ChemCam team came up with to try to get better results on sulfur. And what it does is it takes an average spectrum of your training data and it finds the minima and maxima. And then it just sums up between the minima and assigns that summed value to the wavelength of the maximum. So this is an example of a spectrum. It would be reduced to 2 points instead of the 15 or whatever this is showing. It's just a way to reduce the dimensionality without losing much data. Baseline removal, we have a bunch of algorithms that were provided by a collaborator. So you can play around and choose the one that best fits your data. A lot of different options. Likewise, we have a bunch of options for just manipulating your data, not necessarily changing the values, but just the basic sort of logistical stuff where you may want to read in PDS data, you may want to remove a row or rename it or rename a column or split your data on some variable. You can do all those sorts of manipulations very easily. We also have some outlier removal algorithms from scikit-learn, clustering, a couple of simple clustering algorithms. And all these plots that I'm showing are made in PyHAT as well. So it has plotting capabilities of various kinds. A newer addition, I guess it's not super new now, but our second PDART was to add these end-member identification and unmixing algorithms. These are more commonly used in terrestrial remote sensing, but they're available. This is an example using the Salinas sort of standard data set and trying to find 3 end members. And you can look and see, okay, the spectrum of end member 1 is certainly distinct, and members 2 and 3 are kind of similar. So maybe 2 end members was actually the correct choice for this. You can do unmixing of various types. So this gives you a lot of options that especially terrestrial people are familiar with some of these and will want to use those on their hyperspectral data. And then, of course, regression. Like I said, I kind of started PyHAT as the software I wish I had. And so it can do that stratified k-fold. It can do a bunch of different multivariate regressors. It can do the submodel blending, and you can save and restore your trained models. You can also calculate what we call local RMSEPs. These are what we use, especially in the ChemCam predictions, where when you look at the results on one of these one-to-one plots where you have predicted versus actual, you might notice like there's more scatter in certain areas than other areas. So if you really want to understand how well you're doing for a given prediction, you kind of want a sliding scale on what you report your RMSEP. And so the local RMSEP function allows you to do that and sort of set a window size, and it marches over your test data. And you get a more granular estimate of your accuracy for any given predicted composition. We can also do some spectral parameters. There's some sort of hard-coded spectral parameters for spectral profiler, MCubed, and Chrism, various band depths and slopes and things from the literature. Those are all implemented. There's also some sort of basic processing, continuum removal, smoothing, region of interest selection, and TIFF export. So you can load your cube in, calculate a band depth, and export a geotiff with the same projection information so that you can then load it into your GIS and it'll show up where it's supposed to. And then just recently, something very simple that I can't believe I did not add before, but I finally added it, is just basic band math so you can do your own parameter. So instead of hard coding these things, you can just say wavelength 1 plus wavelength 2 divided by wavelength 3 plus wavelength 4, whatever permutation you want. So I've just added that, so that gives a lot more flexibility so you don't have to rely on what's already hard-coded. So that's PyHAT. It's still in development, but I hope it's a useful tool for people. And I'm certainly open to ideas for how it could be used for other data sets, different capabilities you'd love to see. So just let me know. The final thing I'll talk about is the Planets project. So this is an education project funded by the NASA SciAct program. And amazingly, we are coming up on our 10th year of the Planets project. And it's funded in 5-year increments. So the first 5 years, we developed these 3 units. And the idea of these units is they provide science and engineering activities for students that are interesting and realistic. So for space hazards, this is for a little bit younger kids, grades 3 to 5. They have to learn about hazards on Earth and then learn about hazards that you might face in space and talk about ways to mitigate them. How do you protect your astronauts from a solar flare or from, a dust storm on Mars or whatever. Water in extreme environments. For the science side, they talk about the distribution of water in the solar system, sort of getting at the idea that Earth is not where all the water is, despite sort of the preconception. For the engineering side, they work on a filtration system as if they are on a space station or living in the desert on Earth, and try to learn how to engineer that and remove contaminants from water. And then remote sensing, which is the one I'm going to talk about the most today, is they are the engineering side. They're sort of designing the instruments that will look at data in different ways. These are not instruments, they're like paper towel tubes and pin screens and things like that. But it gets them thinking about the different ways you can make remote measurements. And then the science side is basically a 6th to 8th grade level recreation of the landing site selection process, where they look at different data sets and evaluate them and try to argue amongst themselves about what the favorite data, their favorite landing site is. So that was all sort of done in Planets 1.0. Planets 2.0, the guidance from NASA was, don't develop any new stuff. We want you to improve your previous stuff. And so following that guidance, we opted to take our 3 units and optimize them for a few different key audiences. So our key audiences are English language learners, Indigenous learners, and learners with different physical abilities. So for example, blind kids or deaf kids. And so one thing that's unique to the Planets project from 1.0 and 2.0 is that subject matter experts like us are not just called in at the end to review the final product and say, that's not quite accurate. We are part of the process. We come up with the ideas for the activities. We help refine them. We design the cards that they use in the card games, or design the graphics that they use in the remote sensing activities. And so by doing that, we end up with a much better product, honestly. The educators are experts, and they are really good at reeling us back from trying to include all the science suite they could possibly learn and trying to focus on certain key learning goals. But having the subject matter experts involved allows us to use our science knowledge to think a little more creatively about what the activity should actually be. And it's been really, really useful to, go back and forth between the science experts and the education experts, and come up with activities that really are scientifically accurate, far more than most in class activities, but also are achieving those education goals. They're not too complicated, they're not too hard. And there's a healthy back and forth there, but the end result is really great. So I wanted to talk a little more about the 2.0, and especially something that I've been involved with a lot, which is adapting the remote sensing unit, which is a highly visual unit for students who are blind or have low vision. So how do you do that? How do you give them a bunch of image data or spectral data and expect them to learn what they're supposed to learn the same way that a sighted kid would be able to do? And so this is an example of the orbital maps that we provide for the landing site activity. And you can see on the left, this is a visible CTX and high-rise map, where the only sort of guide is we outline the alluvial fan and Gale crater, because it's really not obvious in the image. And then there's a couple of inset boxes, and one of those is shown over here on the right. For the blind and low vision kids, I made this map where we highlight different geologic features with different shades of gray. And these maps are designed for use with something that I'd never heard of before, but it's called swell paper. And I guess at schools for the blind, they have special printers that you print the image or the text on paper, and then areas that are darker, the paper goes into some sort of oven or something, and where there's more ink, the paper puffs up more, so you get a tactile representation of what's been printed on the paper. And so that's what these maps are for. We take the geologic features in the images and we draw them in a simplified form that will work as the swell paper puffs up and can be used by students with low vision. And so as I was doing this, I kind of realized this is basically, geologic mapping. We're highlighting key features. We're highlighting, just differences and boundaries that are not always obvious to a student who's looking at this. So these blind tactile maps are actually useful for sighted kids too, just to highlight, what is useful to look at in this map. What are key things to draw your attention to, just like a real geologic map would do. It's not quite the same as a geologic map, but it kind of shows this universal design idea where you're designing something that helps everyone. It's not just going to help blind kids, it's going to help all the students. So this on the right is the example of the tactile version of this. Zoom in on the Gale crater right here, the infield channel on the slopes of Gale crater where Curiosity recently has been driving. We do something similar for our other data sets in the remote sensing activity. So this is topography. This one is pretty straightforward. You just get rid of the color and allow the dark line, the topo lines to be raised in the swell paper version. And they can get everything they need from that. The density of the lines tells you the slope. You want to land here, not here, basically. We also do mineralogy. We have mineral maps. And so this is an example. These are very similar. The low vision one is just in Braille, but we give them different textures for the different minerals, and they don't know the minerals. They just know that they're different. And then they are given their mineral fingerprint cheat sheet. And so they get the spectrum from each of these colored areas on the map, and then they have to compare it with the reference spectra to figure out which minerals are in their map. And they can see, oh, this landing site only has volcanic. Maybe if we're looking for water, that's not where we want to go. But it was a real challenge to make all of this accessible for blind kids. And we also got a question from both the educators on our team and the educators teaching the units in classrooms. Why the heck do we need all this infrared stuff? Wouldn't it be simpler to just talk about the visible light? So I made a little video and presentation to illustrate that, because I was very adamant that we need to have the infrared, and I think most scientists will agree. But I made these graphics to illustrate that. So you have your olivine and your pyroxene. They're pretty darn similar in the visible, but then oh, hang on, there we go. And then you throw the infrared on and you can quickly identify them. And so I showed this to the educators and they said, oh, I get it. So that video is available. We provide a lot of support for the educators because we know these units are not being used in the classroom most of the time. They're out of school time, summer camps or after school activities, things like that, where the educator may not even be a science teacher. They may be a college student with a summer job. And so we provide as much information as we can to support the teachers so they feel confident teaching this stuff. And answer questions like this, like why the heck do we need all this infrared? Wouldn't it be simpler to just look at the visible? But this is what we came up with for how do we make these spectra accessible. So the bottom is the Braille version of the top spectrum. So this is an olivine spectrum. We have the visible range and then the infrared range. For the Braille spectrum, all the labels are in Braille, of course. You can't rotate the Braille label because that's just very confusing. So the plot is a little bit squashed. And then just recently we added this is based on an idea we saw at Lowell Observatory where they have tactile displays, and one of their displays shows a spectrum, and in the visible part of the spectrum, they have a varying density tactile bumps. And so we shamelessly stole that idea because it's a great idea. And so now when you print this out on swell paper, the higher frequency, shorter wavelength light has shorter wavelength stippling. And as you get to the red, you have a longer wavelength stippling. So you can actually feel the change in the visible wavelengths as you go. And then we also have, and I don't know if this will work, but we also converted the spectra to audio. And so what we did is we said, okay, the frequency of the audio is the height of the line, the reflectance. So it'll be higher pitched when you're higher and lower pitched when you're lower. And the wavelength is the time of the recording. So I'm going to click this and see if this works. And you can trace along. It also has little beeps, and those are these vertical tick marks on the Braille version so that students can get referenced as they go along. So let's see if this works. Okay, so not the most beautiful sound, but it kind of gets the idea across. It allows you to experience what the spectrum looks like in two ways now. They have a tactile version and an auditory version. So that was a fun sort of project to write the code to generate those audio files and generate these Braille versions of the spectra. Oops, no. Okay.
My dogs were really wondering what was going on there.
I'm
Yeah.
glad we could make it accessible for the dogs too. And then finally, that was sort of the accessibility of the Spectra part, but I also wanted to talk a little bit about this because this was just fun. We, in one of our units, the water in the solar system, we refer the teachers to the NASA Eyes on the Solar System page, where there's this beautiful 3D visualization of the solar system. It's great if you can see. If you can't see, it's right in the name. It's eyes on the solar system. If you can't see, it's basically useless. And so we were trying to think, how can we make something like a tour of the solar system for blind learners to get some of the concepts, the spacing between the planets, the size of the planets. And so we just sort of on a whim, we came up with this, where we created an audio file where the size of the planet gives the pitch of the sound, and how close you are to the planet gives you the volume of the sound. And so you start at the sun and you go flying out of the solar system, and you get this sort of sound effect as you go zooming by the planet that tells you how big the planet is. We won't listen to this whole thing because it would be 35 seconds long and kind of tedious, but we'll go through the inner planets and the first couple outer planets. So each tick, each beep you hear is 1 AU, and the pitch is lower for the larger planets. So let's see if this works. So there's the inner planets. Here comes Jupiter. So you get the idea. We don't have to listen all the way out to Neptune, but that was a little fun way to, it's not quite as rich as the whole eyes on the solar system, but it's something. It allows you to play an audio file and convey the spacing between the planets and the size of the planets in a way that you don't have to be able to see anything. Oops. Okay, so I'll wrap up there. So to conclude, review all the info I've dumped on you. Sort of three areas of focus in my work. Libs quantification. We do these multivariate regression approaches. We're in the process of finalizing new models for SuperCam. We're using an expanded database, this Bayesian optimization, and superlearners, all in an effort to get better, more accurate results that will then be shared with the community, so that we can make the most of the data that we have. And then there's PyHAT. This is the software tool that I've developed. It's free at this link. We're currently working on adding some more I/O support for terrestrial data sets. I'd love to keep this project going. If you have a project that needs software and could fund some development, let me know. I'd love to collaborate and add capabilities that people need to this tool. And then finally, planets. This is this education activity. It's been really fun working with educators and trying to sort of be creative and use our science knowledge along with the best practices for education to design all these units. It's been really cool to be integral to the process. A lot of times you'll get asked to review something at the very last minute, the very end stage, and you say, well, okay, that's fine, but it's not quite right, and there's nothing you can really do about it because it's already ready to print. So being involved from the beginning has really, really helped. And we're hoping to propose for a round 3 of planets. We're all waiting with bated breath for roses to release. So if that ever comes out and SciAct still exists in that release, we're planning to propose for planets 3.0. And we'd love to have more subject matter experts. So let me know if you're interested in that sort of thing. And just to conclude, I'm really looking forward to making the switch over to PSI and joining all of you. And I would love to collaborate on any of this or any other interesting research that you think might be sort of adjacent to this sort of work. So feel free to reach out and chat, and we can hopefully start up some collaborations. So thank you.
Thanks so much, Ryan. This is really great stuff. You're doing a ton of really interesting projects.
Thank you.
Let's see. I bet we have some questions from folks. So please go ahead and speak up or raise your hand. Alex Morgan, go ahead.
Hey, Ryan, that was a really great talk. I have two questions regarding planets. The first is where or how widespread the activities are currently being used, like how that's been deployed. And then I was also wondering, the materials for blind and visually impaired kids are really creative, like the tactile things and the sounds. And I'm wondering, how did you develop those? Like, did you have somebody on your team who was blind, or yeah, I'm just curious as to the process for that.
Yeah, so to the first question, these are used nationwide. We they've the reason it's taken 10 years is we do a lot of piloting. We send it out to schools, after school programs, summer camps, and then the revised product is put on the website for planets. I should have linked it here, but that's accessible to anyone, and so people can download it, and we can keep track of where it's been used, and it's been used in, I believe, every state in the U.S. as well as multiple places abroad. It's I don't know the numbers. It's been used quite a lot and quite broadly, and we have generally good feedback on it. And we're just about to publish these updated versions with all of the accessibility changes and things like that. In terms of how we made the accessible stuff for the blind and low vision kids, we did have a collaborator who is blind. He's in Tucson, actually. And we also had several other team members who have experience working with blind students. One of them was at Space Center Houston for a while and did some accessibility work there. And so I've worked with them to design these. I made all these graphics that I showed and all the audio that I showed. I wrote the code and developed them, but it was with a lot of feedback from people who know what they're doing. So I took what they told me and then made drafts, and then they said, that's a little bit too busy. They're not going to be able to read that, or you can't rotate your Braille labels sideways because that's confusing. And so we iterated on it, and that's how the whole project worked, for the indigenous learners and for the language learners too. We had experts who are members of that community, who know what learners in that community need, and we tried to incorporate their feedback into the projects.
Great. Who else has questions? I've got a couple. Oh, I'm sorry. James, go ahead.
Hi, Ryan. One question occurred to me while you were showing the Braille, the density of the Braille dots for the visible light. Why not include that into the infrared? It's kind of a natural way to show the lower energy as you go to longer wavelengths, right?
Yeah, that's actually a good thought, and I had that like as I was putting these slides together, I was like, what if we just kept it going?
I would keep it going. I mean, indicate somewhere that there's, red light is the end of the visible light spectrum, but then continue with the process, because it's a nice way to show lower energy light.
Yeah, I like that suggestion. I think the issue is just I think it's a limitation of Matplotlib. I was not able to make a smooth transition of density. It's more, you have to set it to one level or another, and you may end up out in the infrared with dots that are so far apart that it'd be more confusing than helpful. But that's definitely a good idea, and something that I should talk to our blind low vision experts on and see, like, do we want to do this or just keep it to the visible? But yeah, I like that.
One other question. I'm sure people have taken lib spectra of various meteorite samples. It's not something I've looked at, but that I don't see how they could not do that. I don't know if you've looked at that sort of data, but I'm just wondering whether people have compared LIBS spectra of meteorites to the observation of meteor spectra, hopefully for a similar type incoming object, because there's a lot of visible emission, as we know, and people do look at those lines, and I'm just wondering how those compare, the lab spectra versus the ablating meteor spectra.
I'm not sure. That's a really cool idea. I know some people on our teams have shot meteorites, especially in the sort of early proving stages of the instruments. I'm not aware of anyone who has compared it with ablation spectra from meteorites, but I love that idea. And I'm kind of excited to try to dig up one of those ablation spectra and see how it
Yeah, we should do that. I know some folks that do the ablation spectra, but I don't do them myself. Okay,
yeah,
thanks.
cool idea.
Yeah, that's really cool. Other questions? Quick one from me. On your last slide, you referred to planets as out of school.
Yeah.
I didn't hear you say that, but maybe you did and I missed it. But what does that mean then?
That means that we are not designing this to be used in class, fitting with all of the educational standards. We still try to tick the boxes on educational standards, but our real target audience, our target classroom, I guess, is not in class. So after school programs, summer camps, informal education, things like that.
Okay.
That allows us to be a little bit more flexible and interdisciplinary. There's nothing that says, a teacher can't take it and use it in class. It's just we are not restricted on what we can include because we're trying to fit into a box.
Yeah. Okay, got it. The other thing I was wondering about is I think I was surprised. I was wondering if your PyHAT can be used for reflectance data. And I was convincing myself that it couldn't because of what I was thinking you were saying it was able to do. But then you said it is used for Prism and M-cube data, for instance, which is interesting because they're so different and those atomic emission features are so narrow, and you've got to really fit the spectral shapes to be able to match them in absorption and reflection. But I guess that's all done through those kind of features that you said kind of at the end there that users can apply.
Yeah, so the PyHAT is very smart, but also very dumb. It doesn't care what you feed it. As long as it's in a CSV format with wavelengths labeled, it will work with it. And then it's buyer beware in terms of what you do with that.
Because then the lab data that you put in to match, I mean, to make the models have to be appropriate for whatever data you're putting
exactly.
in.
If you want to try to do a multivariate regression with reflectance data, you're going to need to load in the whole,
whatever
use the
library,
spectral database or whatever you want to use.
Yeah. Okay.
And there's no guarantee it'll work for that application, but PyHAT will do the calculation for you. And that's part of why we have this user guide that's coming out, which talks about it's flexible, but here's how the different algorithms work and how you might want to use them. So I think it would be really cool to try it with reflectance spectra to do some of these multivariate regression. I'm not convinced it would work because there's so many factors in reflectance spectra that
so you're saying
hard to.
It could be used for MQ, but it hasn't so far.
It can definitely be used for like band depth and stuff like that, because that's just simple math between a few different wavelength channels. So we can certainly do that. If you want to try to apply what we do with SuperCam or ChemCam to reflectance spectra, that's going to be a whole project. You're going to need the lab data, and you're going to need to make sure that your lab data is transformed to look as much like the orbital data as you can, and all of those sort of preliminary steps. And then even then, I'm not sure that these regression algorithms would do a good job on reflected spectra, because grain size and dust and things like that
Yeah.
would sort of, unless that's in your training data, unless you have a database
Yeah.
with every type of mineral, with every level of dust cover and every level of grain size, like that's the sort of level that you would need to feed into these algorithms.
Got it. Yep. And so then you could even do it on icy satellites or something.
Oh, sure. Yeah. And that was part of my motivation to add just the make your own band parameter, sort of simple band math stuff. Because, it was a real pain to do what was in Lisa's proposal to hard code all of those algorithms, when we could have spent a couple hours writing these sort of granular steps where you can make your own. Just, take the sum of these, and then that becomes a new column, and then you take that and do a ratio, and you can make an arbitrarily complicated band parameter using these little simple steps. So yeah, I'd certainly be excited to use PyHAT with other data sets, outer planet data sets, things like that. And I'm happy to work with people if you have a data set that you want to use with it, but you don't know how to get it into the right format. I'd be happy to help out with that and figure out how we can make it work.
Yeah, really neat. Let's see, Ryan, I don't know if you can see the chat, but there's a couple of, not questions, but at least just comments in there that you might want to see, or I can
bring it up. Okay, I think I got it here.
It's really just kind of comments, but
let's see. So I scared someone's cat. Okay.
Are there any more questions though from PSIers out there? I think we are basically at the end of the time anyway, and people are having to run off. But
Yep.
Ryan, I want to thank you again for being here. This is really fascinating stuff, and we appreciate you sharing it with us.
Well, yeah, thanks so much for having me. I'm looking forward to working with everyone.
Great, thanks. Bye, everybody.
Bye, everyone.